Again, it's a rich thing.
What is going on, guys? Welcome back. In today's video, we're going to talk about something very interesting, but also something quite technical. And we're going to get right started. Let me open up Python 3 here, and I'm going to show you something. Now, what happens when we type something like 1 plus 2? Obviously, we get 3 as a result because that's the result of the calculation. But what happens now if we type 0.1 plus 0.2? Well, the result is not 0.3, and this is what we're going to talk about today. Why is this the case? Why is 0.1 plus 0.2 not 0.3? And also, why is 0.8 plus 0.4 not 1.2, but something else? So it's almost 0.3, and it's almost 1.2, but it's not quite exactly that number. And if we go ahead and say 0.1 plus 0.2, actually, let me put that in parentheses, 0.1 plus 0.2, does that equal to 0.3? And Python says false. And in today's video, we're going to talk about why this is the case. Now, in order to understand why this happens, we need to understand how floating point numbers are represented in computers. And remember that computers only know zeros and ones. So no matter what you try to represent, be it a high-level software, be it an image of a car, or be it floating point numbers, everything boils down to zeros and ones. And because of that, we need to be a little bit creative when we decide on how we represent floating point numbers in computers. Because for integers, it's quite obvious. We have an integer, for example, 24, and in the binary system, this is just represented by using powers of 2 that we add together. So in this case, this would be 16 plus 8, because that is 24, and this would mean a 1 for 16, a 1 for 8, a 0 for 4, a 0 for 2, and a 0 for 1. That would be 24 in the binary system. Now, for this video, since it's quite technical, you need to understand the binary system, at least on a basic level already. I'm not going to explain all the basics because that would just take too long. You need to know why 24 equals 11000. If you don't understand that, that video is a little bit too advanced for you. So I would go and catch up on the basics and then come back to this video. So for integers, it's quite simple. For floating point numbers, it's not that straightforward. So how do you want to represent something like 8.9167, for example? And what we did in computer science, or what other people did in computer science, is they came up with the so-called IEEE-754 standard. This is a standard for representing floating point numbers. It is a structure that is, chosen to represent floating point numbers. We agree on that, and different programming languages, different systems, different architectures use that system to represent floating point numbers. And the system is, as I said, quite technical, but we're going to cover the very basics of that system. What you also need to know is that Python uses double precision floating point numbers. So we use 64 bits to represent floating point numbers. In other programming languages, you have the ordinary float, which is 32 bits, and the double, which is 64 bits. In Python, we only have float, and this is the double, actually. So we have 64 bits. This is a different representation. This is why this is important. And of those 64 bits, let's write it down. We have 64 bits. The first bit is the sign. So the first bit means, is this number a negative number or a positive number? Because we don't want to only be able to represent 0.9 and 0.1456 and 0.236. We want to also be able to represent negative numbers. So what we're going to do here first is we have a 0 for positive numbers, and we have a 1 for negative numbers. This is what the first bit indicates. If the number starts with 1 and then something, okay, maybe just zeros and ones, then something, this is basically a negative number. And if it starts with 0, it's a positive number. The next 11 bits are for the exponent, because we don't just represent the numbers by, just writing down one part of the binary dot the other part of the binary and then a sign in the beginning. But what we do is we have a certain formula that we use to calculate the floating point number. So we use an exponent. I'm going to tell you in a second what this basically means. And the rest of the bits, those are, as far as I know, let me just look it up, the next, what was it? 52 bits. The next 52 bits are used for the so-called mantissa. And how do we actually now represent a floating point number. Let's do an example. I have prepared some examples here. Now, first of all, let's represent an ordinary integer, so not a floating point number, because that representation also works for a basic integer. Let's try to go with this one here. There you go. So this is one of these numbers, for example. We have 0, which is the sign, we have this as an exponent, and we have this as the mantissa. Now, one thing that you need to understand about the 64 bits, about the double precision, is that we always have to subtract 1023 from the exponent, because that allows us to go also into negative exponents, which allows us to go to very small numbers and also very big numbers. And in this case, what we have here is we have 0, so it's a positive number. We have this exponent, which is 1026, which basically means that when you subtract that number from that number, you end up with an exponent of 3. Now, this exponent is now taken 2 to the power of that exponent, and then we multiply that with 1 point the mantissa. Now, it may be confusing, so let me explain this once again. The first bit signals that this is a positive number, so we know, okay, the sign is positive. Then we take the exponent. If you take that number here, this is a binary number, and you convert it to decimal, you will end up with 1026. From that, you subtract 1023. That's just the definition of double precision exponents. This is just something that you have to know. Then you end up with 3 as a result here. You take 2 to the power of the result, in this case 3, times 1 point the mantissa. Now, we don't just calculate that, but we think about these 2 to the power of 3 as shifts, because we're dealing with a binary system. So this means that from 1.01, which is 1 point the mantissa, 0, 1, we basically just say shift 3 times to the right. So 1, 2, 3, and we end up with 1, 0, 1, 0. This is 10. So this number represents 10. Let's make another example with an integer, and then we're going to proceed to the floating point numbers. Let's say we have this example here as well. We have, again, a 0, which means positive number. We have this exponent here, which is 1027 minus the static 1023 is 4. So we shift 4 to the right, and the mantissa is 1.1. So we shift 1.1 to the right 4 times, and we end up with 1, 1, 0, 0, 0, which is 16 plus 8, because this is 16, this is 8, and this is 24. All right, so now let's look at floating point numbers, because there things get a little bit more confusing. I'm going to copy here an example of 1.5. There you go. 1.5. We have 0 again, so it's a positive number, and this time the mantissa is, the exponent, is that. The exponent is 1023. So basically, we subtract 1023, and this ends up being 0. Basically, we don't shift at all. Now, we still have the mantissa, so it's 1 point whatever is here, and in this case, just 1.1. And now we need to interpret this 1.1 in binary. Now, 1 is 1, so the left part of the comma is just 1, and the right part is now taken 2 to the power of negative 1. So what we usually do in a binary system is we have some number. Let me just add a comment. We have some number. And what we do is we take 1 to the power, 1 times 2 to the power of 0, 1.2 to the power of, of 2, then to the power of 3, and so on. I just noticed that I have an error here. This is 2 to the power of 0. So we basically take this 1 here, which is just 1 because it's 1 times 2 to the power of 0. And when we go after the comma, we do it the other way around. So we don't go up, we go down. So in this case, 2 to the power of negative 1. And if you put that into a calculator, this is 0.5. And if you add 1 plus 0.5, this ends up being 1.5. Now, I want to mention here that you only need to get this, you only need to understand this in detail if you really care about the technical details. You can still understand basically why the error happens if you just understand that we represent numbers like this. So we're going to now do something. We're going to leave this as a comment here, and we're going to now see what the actual representation is of the individual numbers. Because if we print 0.1 in Python, and if we print 0.2 in Python, and if we print 0.3 in Python, we're going to see something that's not quite correct. So if I go terminal, terminal bash, we're going to just say Python 3 main.py, you can see that this is the result. Those are the representations. However, that's not quite the result. That's not quite true because we saw that 0.1, 0.2, the sum does not equal to 0.3. Now, if we actually want to see what 0.1 is, we can go ahead and print an f string and say that we want to have a precision by just saying colon and then point, for example, 60f. This would give us 60 decimal places. We can copy that and do the same thing for 0.2 and 0.3. Now we're going to run this again, Python 3 main.py, and you can see that those are the actual numbers. So whenever you type 0.1 in Python, this is what you're actually working with. And if you type 0.2, this is what you're actually working with. And if you type 0.3, this is what you're actually working with. And now we can see why this happens, because if I say 0.1 plus 0.2 and I want to know the exact result, I go back there and I run this again, you can see that 0.1 plus 0.2 is actually this, whereas 0.3 is actually this. So it's not the same value. This is why Python says it is not true that this is the same value. And in order to understand why exactly this happens, this is now going to get a little bit technical again. We're going to use the struct library of Python to actually represent this as a IEEE representation here. So what we're going to do is we're going to say the number that we want to represent. Let's start with 0.1. We're going to calculate the binary representation, and this is basically just going to be struct.pack. And the first thing that we pass is a string indicating what we're actually looking for, and then the number itself. And the string is going to be double precision with, I think it was big endianness that we're choosing with the greater than symbol. And then what we do is we say binary representation dot equals join, and what we're joining here is basically an f string where we take b and then 08b. This is just a format that we're going to use. We need to use that in curly brackets, and then we say for b in binary representation, so for the individual bytes. And then we should have a string. The only thing that we need to do now is we need to split it up so that we have this representation. So what we want to do is we want to say binary representation is going to be binary representation, the first thing. Then we want to have a space. Then we want to have everything after that, or the next 11 bits after that. So 1 to 12, then another space, and then the rest. So 12 until the end. All right, so this is the binary representation. Now we can just go ahead and say print f0.1 is, and then the binary representation of that. So that should be enough. Let's go ahead and try the terminal split again. There you go, Python 3 main.py. And you can see that this is the actual representation of the number. Now we're not going to go through the calculations again because this is a pretty large mantissa here, but we're going to do something else. We're going to just go ahead now. Come on. We're going to go ahead now and let me just delete, or actually let's keep that. We're going to remove this part here so it's not confusing our output, but we're going to copy that and we're going to do the same thing for 0.2 and for 0.3 and also for the sum of 0.1 plus 0.2. So we're going to change this to 0.2, we're going to change this to 0.2, this to 3, this to 3, and this is going to be whatever the result of 0.1 plus 0.2 is. And here we're going to just say sum is. There you go. Now terminal again and Python 3 main.py. There you go. So now you can see what the problem actually is. 0.1 and 0.2 have the exact same mantissa in this case. And the reason for that is you can see where the error is actually happening, because the error is not necessarily happening everywhere with every floating point number. But the problem here is that we have a repeating sequence in here. We have 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, and so on. This is just periodically going on. But the problem is we only have 64 bits, which means that sooner or later we're just going to have to cut it off. And in this case, you can see that this happens here in the end. The sequence is cut off, and this happens also for 0.2. And because of that, we don't have the exact number stored because we cannot represent the exact number. We cut it off in the end. And this is why the result actually of that, when we add the two things, when we perform the addition, we're not going to get the accurate result because we don't store the accurate number in the first place. 0.1 is not actually exactly 0.1. 0.2 is also not exactly 0.2. And this is just because those are not powers of 2. And because of that, we get this error here in the mantissa, and this is why 0.3 is actually something else than 0.1 plus 0.2, because 0.1 and 0.2 are not actually what we're working with here. All right, so now let's talk about solutions. What can we do in order to solve that problem? Because if you go to the Windows calculator, you're going to see that the Windows calculator does not have the problem. If I type 0.1 plus 0.2, you can see that 0.3 is the result. So it's not something that computers cannot do. Now, of course, one thing that you can do is you can just round, because as you saw, 0.1 is not exactly 0.1, but it's kind of 0.1, and the result of 0.1 plus 0.2 is not exactly 0.3, but it's basically 0.3. So what you can do is you can just cut off after a certain amount of decimal places. But what you can also do is you can use the decimal module in Python. So you can say from decimal import decimal with a capital D. And by doing that, we can create the individual numbers. Now, first of all, we can see that if I type decimal, print decimal 0.1 like that, you're going to see that this gives me a different result, Python 3 main.py. You can see that here I immediately get the representation without having to specify some formatted string. But what I can do here in order to actually get the accurate representation here is I can pass a string with 0.1 here, and I can pass a string with 0.2 here, and I can pass a string with 0.3 here. And then we can also print, or actually let me create variables for those. So we're going to say this is 1, this is 2, this is 3, and then we have a result. It's going to be 1 plus 2. And now we can print all of these here. So we can print 1. Come on. We can print 1. We can print 2. We can print 3. We can print the result. There you go. And now we can see what happens when we run this again. You can see that the result, so 1 plus 2, 0.1 plus 0.2 in this case equals 0.3. And we can also solve another problem, because a problem that we haven't looked at until now is that we also have rounding errors sometimes. So because of the exact same reason that we have the error in the addition, we also have rounding errors, because if I have the number, for example, what was it? If I try to print round, the basic round function, and I try to round the number 2.675, for example, 2 decimal places, what I will get as a result, let me just comment all of this out here so that we don't get too much output. What we're going to get as a result here is 2.67, which is not true because 2.675 should round up to 2.68. Now, if I don't pass this, but if I pass a decimal here, so if I say 2.675 as a string here, and I then do that, you're going to see that we get 2.68 as a result. So the decimal module or the decimal object allows us to be accurate here when it comes to floating point numbers. So that's it for today's video. Hope you enjoyed and hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you very much for watching. See you in the next video, and bye.